Okay, I'm making a video for many of the students who are going to miss class because of the inauguration. We're going to talk about relative motion and dependent motion. Relative motion will come back to us in vector form. Today we're going to do one-dimensional. So I just want to bring this up. When we talk about relative motion, it's sort of an obvious thing in terms of something we intuitively understand. If we're driving in a car down the highway and we have some jerk driving by us and passing us, our perceived velocity of that person is relative to us, right? So usually what we have is that what we would say in terms of a position, that would be the distance between us. If I am B and I look at A, the relative position between us is B with respect to A. So that's the way that we refer to that, B with respect to A being the reference. Okay, so rewritten another way, this is how we like to write it. We say that, okay, where is B located? Well, it is where A is the reference, and it's B with respect to A. I think I said it backwards. I believe that we would be A, and we're looking at where B is, so the B with respect to A is going to be this, and quite often we will say, well, where is B? B is, well, wherever we are plus wherever the reference is. Okay, so hopefully I didn't say that backwards. So if we take the derivative of this right here, if we take the derivative of it, we will find that we get velocity of B is equal to the velocity of A, that's our reference, that's like us in the car, and the velocity of B with respect to A, that's what our perceived delta speed. So if it looks like the person passing you is going 10 miles an hour, relatively speaking, and you were going 50 miles an hour, they're going 60 miles an hour, okay? So you are 50, they're going 10 miles an hour faster, and are therefore going 60 miles per hour. And the same thing can be done for acceleration. Now this will come up again later. I think today, though, we're mostly, and for the homework, we're going to go on dependent motion. And what is dependent motion? Well, that's the relationship between points that has some type of bond between them. So they're physically tied together. We use most of the time for our discussion, we use like a cable that's going to be between them. And we go through a procedure where we create a reference datum, right? And I'm going to use these circles right here. I'm going to use these numbers and try to be consistent with it. So our reference for each of the different points, we're going to use this pulley as a good place to start from. So our reference is going to be from this pulley, and we're going to have two different axes here. And we're going to define what is positive as going away from that datum. So that the position of the pulley right here is going to be something we can call SA, for instead of using X, because it's not all horizontal. We're really, even though these appear to be in two dimensions, we're really treating it like it's a one-dimensional thing, because when it moves in one direction, the guy moves in the equal amount, in this case, right here. So we're going to set, this is the way we set the thing up. So we say, oops, that's going to be B. We have the distance away from that datum, SA, in this direction. We're going to define positive SB in this direction. And it's going to be okay as long as we're consistent about this, we'll be fine. So I'll just write that that's the datum that we have. That means that's the reference. Okay, so we want to write an expression in step 2 for the length of the cable in terms of these position coordinates, right? So here is position 2 right here. And so we go for the total length of this cable. We're going to say that that's going to be L for right now. When we know that the length of the cable is not going to stretch, so just be aware that that's a constant, okay? And that length of the cable is going to be equal to SA, so right up here, SA, plus SB. All right, so that length. And then we also have, let's just to be complete, we have 1/4 of the circumference of the pulley. All right, so don't belabor this too much, but we have also happen to know that that too is going to be a constant right here. Now, step 3, we take the derivative of this equation that we've just written. And we take it twice, right? First, we're going to take it with respect to time. So we say d dt of the above. That's going to be 0 because the length is constant. So we're going to have, now we're going to have the velocity VA of this point right here plus the velocity of B. And then, of course, it's going to be plus 0. Right? So what we've done right here for this expression is we said that velocity of A is equal to negative velocity of B. That's what we've said up in this equation right here. This is a relationship that we know. And that's, of course, that's positive and negative depending on what we assigned as our datum. So if A starts to move to the left right here, right? So it has a velocity of 1 going to the left, then we're going to have a velocity of -1, according to our datum, of B. Okay, you see how that works? And then now if we take another derivative of the one above, we would say that, okay, the acceleration of A plus the acceleration of B is going to be equal to 0. Of course, we have the derivative of 0. So that's the game that we play. So we need to see this in several different examples before we kind of own it. And you have to try it yourself. Now I'm going to start off, I'm going to include all the constants in this example, and then we're going to go ahead and get rid of those. So first off, I'm going to make my datum right here. So that's going to be 1 right here. So this is that step 1 that we did. And I'm going to start having dimensions. So some of these are already labeled for us. XA is going to be mixed there. I went ahead and used X instead of S. I don't know why I changed. We'll also mention, okay, we'll call this right here, we'll call this H1. I'm calling it H's just to keep it separate because we're going to see that that distance is going to be constant, right? So just bear that in mind. I've also called this XB already. I believe, by the way, these are examples that are in the textbook, which is Beer, Johnson, and Cornwell. This is from the 10th edition. I encourage you to buy the book, right? So I don't want to be copyright infringement here. I don't want you to not buy the book simply because I've written this down. All right, so we have another constant right here. I'm going to call this H2 that's in between here because we know that it never changes between these points E and F and B. So let me write this out. I'll write, once again, we're going the long way around just to show you as an example. And in the next example, I'll get rid of doing some of these. So take a look at the distance between A and C. I want to get the length of the cable. Once again, that's the step 2, is we find the length of the cable. So the length between A and C is going to be XA, right? Minus H1. So that length of this cable right here is that XA minus that H1. And now let's add in the arc that's between C and D. I'll just write that CD to represent that arc that's around the pulley. Now I'm going to add in the cable that's between D and E. That's going to be XB minus H1 minus H2, right? So that's going to be this XB, this total length, X down to XB, and we're going to subtract out H1, and we're going to subtract out H2, and that's going to give us D to E. So let me label this DE, and I'll label this one right here. It's going to be AC right here, okay. And let's see, I don't know if I fit this in here. I think so. I can get EF. That's going to be around this arc right here. And now finally, I'm going to get the length of FG. So plus, and I'll go XB, right, minus H2. Okay? And of course, that's going to be FG. A little weirdness in there. Okay, so I can go ahead, if I want to here, I could just go ahead and lump all the constants together. I could take this H1 and bring it over here and subtract and add it, I guess. I could take the H1 and H2 and H1. I could take the CD and the EF. I could lump all those together and say that, well, this is going to be XA plus, and now it ends up 2 times XB, right? And now for step 3, we take the derivative of it, and we say that's VA plus 2VB, right? And then we take the derivative of it, and it's going to be AA plus 2ab, acceleration b. And therefore, the velocity of A is equal to negative 2 times the velocity of B. And the acceleration of A is equal to negative 2 times the acceleration of B. So we can see this relative motion type of thing. Now let's do another example, but this time we're going to do it without the constants. So what I'm going to do is I'm going to set my datum now right from here. It's going to be maybe a better way to set my datum. So instead of, I'll cross out these guys right here because they don't matter, right? So that's going to be my datum is between here. And maybe I'll go ahead and I'll use my reference instead of this part right here. I'll just take my reference to there. And I'll just take my reference. Let's see, I'll take my reference over here to this. I'll cross that out. And I think that'll do. Okay, this reference is fine. So I say, okay, what's my total length? I'll say it's equal to L, and then this. So I say, first I'll just march through here and say, okay, I want to get this length right here. That's XA. And then this length right here. Okay, that's another XA. This length right here, that's an XB. This length right here, another XB. And this length right here, that's XC. All right. So I could just lump these together, XA plus 2 times XB plus XC. And then I take the derivative of it, and I say, okay, that's 2VA plus 2VB plus VC. And then also 2AA plus 2AB plus 2AC. Okay? So these are equations that relate these motions together. I'll mention that we don't have enough information right here because this says several degrees, 3 degrees of freedom, only 2 equations. So we would need to know an additional thing to be able to get and find out any particular velocity going on. Now here's an example with numbers, okay? Or no, I guess do we have numbers? Yes, we have numbers. So if we're given the velocity of A, this VA, is equal to 2 meters per second, and they're pointing it downwards, we want to find the velocity of E, right? And we don't know if it's up or down. So we have to be careful with our signs here. So let's start this. We'll start with a datum that's right here, and I'll just go to down here for my XA. And then for here, and I have to fit this in here, I'll go down to XB. For here, I'll go down to XC. And here, I'll go to XD. Okay? And I'll look at the thing, and I say, and notice there's 3 cables. So you need an equation for every cable. We need to do this for every cable. So we'll go length of 1 is going to be equal to XA, right? So we have this right here, plus 2 times XB. We can just look at that and say, okay, we have this length and this length. Okay, so that's one equation. Length 2 is going to be XC minus XB. And let's see, where is that? Okay, well, this is the length that we want first. We say, okay, this XC minus XB, that's this part of the leg. And now we have to add in XC right there, right? This relationship, XC. So that ends up being negative XB plus 2XC. Length 3 is going to be XD minus XC. That's this length right here. So I subtracted C from D plus XD right here for all this length right here. And then, of course, that's going to be minus XC plus 2XD. Now, for cable 1 right here, we're going to take the derivative, and we'll find that it's equal to VA plus 2VB. Therefore, VB is equal to negative 1/2 VA. Now, we already know VA, so that means we know VB is going to be negative 1/2 times the 2 meters per second, or it's going to be negative 1. Be careful with the sign. Remember, our datum made positive this direction, positive downwards. and we said that it starts out VA is downwards. So by being negative VB, we're actually going to say later on that VB would be going upwards at 1 meter per second. Now we go to the cable 2, so I'd label this cable 1. Now I'll move over to here where I got room. Cable 2, we say take the time derivative of this equate the length up here, and we find that's going to be 0 equals negative VB plus 2 VC. Therefore, VC is equal to 1/2 VB, or 1/2 times -1, or so it's still going to be negative 1/2 meters per second. And then we take cable 3, and we say that take the time derivative of this guy, and say that's going to be equal to 0 negative VC plus 2 times VD. Haha, make a joke every single time that happens. VD is equal to 1/2 VC, which is equal to 1/2 negative 1/2, or negative 1/4 meters per second. So that's the velocity of D right here. And we happen to know that has to be the same thing. Velocity of E has to equal the velocity of D. There's nothing that could stop it from doing it. And that's negative 1/4 meter per second. So we want to give the answer, though, with an arrow. And we happen to know that negative is negative for our datum here. So we could say that it's 0.25, right? Turned it into there with a 0. Let's make it 3 sig figs meters per second up, and that's the answer. Now, lastly, we have an example here. I'm not sure where that came from. It's got a little bit of a twist to it. You have to think it through a little bit, because now the length of this thing is going to be changing, actually, because it's being wound up from a motor. So first off, let's try to find, we can make a datum, I guess, that I'm going to make. And so I'm not going to use this. I'm going to use coming down this way, make that plus. And I'm going to take the length of this cable is going to be equal to the square root, if you take a look at here, notice that this is 4 feet right here, of SA, I guess I decided to use S this time, squared plus 4 squared, right? It's because we're trying to find this length right here, the hypotenuse. And then plus SC right here, which is measured from this datum. I'm really messing the thing up there. But anyway, okay, so that's going to be SC. Take the derivative of this length, right? So the cable is going to the motor at this instant. Okay, so because it's at this instant, right, that let's say that length has not changed, okay, because it's instantaneous. So when we take the time derivative of the thing, it's going to be equal to 0, right? But a moment later, it's going to change. So is that correct? I think so. This is a weird example. All right, anyway. Take 1/2, right? So because I'm going to say, actually, we could have written this plus 4 squared raised to the 1/2 is going to be equal to SA squared plus 16 to the negative 1/2. And then we say that's going to, but we also have to multiply by what's on the inside. That's 2SA times VA plus VC. Okay, so those are the velocity of the thing. Yeah, I think so. I think that's correct. And now we could turn this thing around and go SA times VA divided by SA squared plus 16 to the 1/2 plus VC equals 0. Okay, so we can arrange that thing together, and they say SA is equal to 3 feet, and VA is equal to 2 feet per second, and I guess they're saying that's upwards, right? So that would be negative for us, right? So when we put this out, that's going to be negative 2 feet per second. And I don't know why we have these symbols around here. If we're getting a direction arrow, I'm going to reconsider this problem. That's okay. Never, it doesn't matter. It's supposed to be representative. So we don't do any other problems where we change the cable length. But I'll stick in the numbers here, -2, and we'll say that it's 3 squared plus 16, 1/2, and we get 1.200 feet per second. And because it's negative, is it negative? I believe, okay, no, we have negative, negative right there, negative, negative. So therefore, that's why that's positive. So VC is equal to 1.200 feet per second. Actually, I didn't need that extra 0. Feet per second downwards. And then we could take the derivative of this up here again, and we could say, oh, this is a long one, equals 0, -1/2 SA squared plus 16 to the -3/2 times 2 times SA squared VA squared plus SA squared plus 16 to the -1/2 VA squared plus SA squared plus 16 to the -1/2 SA A plus AC. Now, how the hell did I do that? Okay, because I guess what I've said up here is I'm taking the derivative, time derivative of that. So that's why we have this acceleration right here. This guy, we need, okay, because we need to do the individually, yes. So we need to take SA, right? So we do it in parts. So we have to take of each one we had to do. All right, so that's why we've separated out. So just look at it carefully, and you'll see that it's valid. VA squared divided by SA squared plus 16 raised to the 3 halves plus VA squared plus SA AA over SA squared plus 16 1/2 equals -AC. So we could find that if we put the numbers in, that AC is going to be equal to -1.112 feet per second squared, and therefore AC is equal to 1.112 feet per second squared, but it's negative, therefore it's going upwards. Okay, well, hopefully that helped you out. And once again, I think there might be an issue with the logic that was placed when this thing was written, because this, I don't think that this length can be considered to be constant, because it is varying with time and it can have a velocity. I don't think that you can take the derivative and say that's equal to 0, but I'm going to go double check on that. Anyway, it's the spirit of the problem relative instead of the actual problem in this case. Boy, that's not a very good example. But I'm going to go ahead and leave it on the video, because it was the rest of the class is going to be hearing this example as well, and I thought perhaps it would help the students on the trip. So have a safe journey back, and see you soon.